Good afternoon. Stephen Elliott of Coherent Breathing. It's August 10th, 2025. Today we will be covering coherent breathing principle number 10. That being, it is proper to divide heart rate variability into what I refer to as breathing-induced changes in heart rate versus changes in heart rate for other reasons. I state it this way because for me, in the beginning of the coherent breathing journey, it took me a long time to understand literature about heart rate variability, the phenomenon, what it is, and how to go about measuring it. This was mostly because the technical papers were rather hard to understand in terms of the numerical analysis and statistical analysis of what they were studying. And secondly, the popular literature on the subject was wrong and confusing. And I have to admit that it took me several years to wrap my mind around what was being discussed. And what I found was that what was really of importance was changes in heart rate due to breathing. And in particular, the changes in the heart rate and really the circulatory system at large as a consequence of what we call resonant breathing, coherent breathing being a specific form thereof. So many I know now are still confused by the terminology heart rate variability. What it means is the change in the heartbeat rate moment to moment. So if we're measuring the heartbeat rate continuously with an instrument like Valsalva Wave Pro and graph that in time being the x-axis, we will see the heart rate varying along on the y-axis in keeping with the intervals on the x-axis. In other words, the heart rate is changing with time. Now, if we have not trained our breathing to be slow, deep, and rhythmic, i.e. resonant or coherent, then when we monitor our heart rate and plot it and graph that either in real time or thereafter, we may see a pattern that is not rhythmic and not sinusoidal. In fact, it can be very arrhythmic. And a very arrhythmic heart rate variability signature is symptomatic of a few things that we should be interested about. One, it is the Framingham study discovered, I think unexpectedly, that heart rate variability is an indicator of all-cause mortality. And the examples I like to use are, for example, crossing the street and falling into an open manhole. Now, why would heart rate variability be an indicator of the risk of falling into an open manhole? Consider that question for a moment. The answer is because the mind is wound up somewhere else and not present, not paying attention to circumstances not paying attention to where we're going, maybe not paying attention to warning signs or safety cones, whatever what happens to be. Now, the same is true for driving. Having a low heart rate variability increases the risk of having an accident while driving. When I had my life insurance physical exam, which the examiner came to my home, this was in 2002 or so. I was upping my life insurance policy at the time. They connected me to a EKG monitor and recorded that EKG, which did record my variability in my heart rate. And I asked the examiner, I said, "Are you recording my heart rate variability?" And she looked quizzical. I said, "It's an interest of mine. I was just curious." But I'm sure that, in fact, they were, because it's a key component in the figuring of mortality risk for life insurance purposes. Now, why would this be? What I began to understand over time was that it is an indicator of our breathing, and specifically how our breathing is contributing to our overall health, primarily by influencing the way that blood flows in our body, and consequently the way that the remaining 37 liters of fluid in the average adult body also flow. This includes lymphatic fluid, cerebrospinal fluid, ocular fluids. All the fluids in the body are compelled to move via the blood flow, which, when we are breathing in a resonant manner, looks like a rooster comb. You may have seen graphics of the Valsalva wave. The Valsalva wave, when rising and when falling, looks like a rooster comb. But in particular, when we're exhaling and the wave is building, and then as we're inhaling and the wave is declining. This rooster comb is the wave below the heart rate, or the heartbeat, is the large change in blood volume, depending on where we're measuring, whether that's the earlobe or the fingertip. And then atop that is the heartbeat writing. It's pulsatile. So we see a large, slow wave rising and falling. And on top of this large, slow wave, we see the pulsatile heartbeat rising as the breathing wave peaks and falling as the breathing wave declines to its valley state. So as we exhale, the breathing-induced wave rises and falls. And as we exhale, the heart rate synchronizing with that, the heart beats rise in amplitude. However, the heart rate is slowing. And then as we inhale, the heartbeat amplitude declines and the heart rate speeds up. This is because as we are inhaling and exhaling, we are emphasizing the venous or right heart circulatory aspect. And as we are exhaling, we're emphasizing the arterial or left heart circulatory aspect. Blood flowing, as you've heard me say many times, in a circle, unimpeded. So as we learn to breathe coherently, this is how it works. Identically to a pendulum, as you heard me say a lesson or two ago. A pendulum is a resonant example of a system. And that same resonance applies really to all physical structures and all biological organized systems like the human body. So when we learn to breathe coherently, what we're doing is really putting the resonance of the human body to work for the good. And by that I mean for health, well-being, performance, and longevity. And it accomplishes this by facilitating more blood flow in a given 60 seconds. The accepted rate at which the 5 liters of blood in the average adult body flows is 1 time per minute. In other words, that 5 liters, if we were to track it around the human body from start to finish, it would circulate throughout the arterial and venous and of course the pervasive capillary circulation 1 time in 60 seconds. I posit that when we are breathing resonantly, where the very act of breathing, the very act of the diaphragm moving downward and then upward is doubling the rate of blood flow in the body per minute. So, in other words, the 5 liters of blood flow in my body when I am breathing coherently is circulating twice per minute instead of 1 time per minute. And in particular, I always emphasize this, and in particular, the blood flow to the brain. This is because each time we exhale while breathing resonantly, it sends a large wave of blood in and through the brain. We'll talk a bit later about how the human body mimics that of the giraffe. Well, I'll leave you with the thought that if the giraffe had not evolved to have the largest diaphragm of any land-dwelling species, that it would not exist as it does today with its extremely long neck. A physiological arrangement, an anatomical arrangement that scientists before my foray into giraffe circulatory physiology did not understand. I don't know that they understand now. The quizzical part of it was that for its body mass, the giraffe heart is calculated not to have the capacity, the pumping capacity to move blood up the 12-foot neck of an adult giraffe. That there was no way that the giraffe heart could propel blood up the neck to the brain, which is necessary, of course, for the giraffe to exist in a scientifically valid way. But what was being overlooked is the fact that the thoracic pump of the giraffe, the largest thoracic pump of any land-dwelling mammal, is huge. And when you hear it breathe, it sounds like a freight train. I had the good fortune of experiencing that breathing about that far from a giraffe's nostrils at the Dallas Zoo. But that's for another principle of coherent breathing. And I'll save that story for then if you haven't already heard it. So thank you for your attention today. Be not confused by the term heart rate variability. It means the degree to which your heart rate is changing when you breathe, ideally, slowly, deeply, rhythmically, resonantly, coherently, relaxing deeply with each exhalation. And with that, I'll leave you for today. Thank you for your attention.